This is Dr.S.Prasanna, Assistant Professor of Mathematics in Pingil Government College for Women, Warangal. In the previous video lesson, we have learnt two concepts, span and the subspace spanned by a set. In the definition of span, we have seen that if v1 bar, v2 bar, so on vp bar are any set of p vectors, then the set of all linear combinations of v1, v2, so on vp is denoted by span of v1, v2, so on vp, and it is called as the set spanned or generated by v1, v2, so on vp. And in other way we can also define the same word span as if v1, v2, so on vp are any set of vectors, then span of v1, v2, so on vp is equal to set of all gamma bar such that gamma bar is equal to c1 v1 bar plus c2 v2 bar plus so on plus cp vp bar. Here the coefficients c1, c2, so on cp in the linear combination are scalars which are taken from the set of real numbers. So in the definition of subspace spanned by a set, we have seen that if H is a subspace of a vector space V, then a spanning or generating set for H is the set consisting of the vectors v1 bar, v2 bar, so on vp bar in H, such that H is equal to span of v1 bar, v2 bar, so on vp bar. And then we have proved a theorem based on these two definitions of span and subspace spanned by a set, and which goes like this: if v1 bar and v2 bar are in vector space V, then H is equal to span of v1 bar, v2 bar. The span of those two vectors is a subspace of V. So we can understand that span of a finite number of vectors which are taken from the given vector space V again forms a subspace, again forms a vector space which is a subspace of the vector space V. So that is how we have even extended this theorem to more vectors, more than two vectors, and came to a generalized notion that if v1 bar, v2 bar, so on vp bar are any set of vectors in V, then span of v1, v2, so on vp is a subspace of V. And after proving this theorem, in the previous video lesson, we have solved some problems based on this theorem, based on the concept of this theorem. And now in today's video lesson also, we are left with some more problems to solve which are also based on the same theorem. So maybe the models are a bit different, but basically all the problems in the span or subspace spanned by a set are based on the somehow based on the theorem only. So now we are at solving the problem number 7. So let us go through the problem now. Let v1 bar, v2 bar, v3 bar so are three vectors defined as above in sixth problem. So whatever be the vectors given in sixth problem, consider them in this problems number 7 also. And w bar is equal to, it is another vector given as 8, 4, 7. It is a column vector given as 8, 4, 7, and we are asked to find that is w bar in the subspace spanned by v1 bar, v2 bar, v3 bar, and if so, what is the reason? Why? If so, why? These are the questions asked for us. Now it is said that in the problem v1, v2, v3 are the three vectors to be considered from the problem number 6. So I have written here the vectors v1 bar, v2 bar, v3 bar which are given in the problem, sixth problem, which is the problem we have already done in the previous video lesson. So there the vectors v1, v2, v3 are given in this manner. v1 is equal to 1 0 minus 1, v2 is equal to 2 1 3, and v3 is equal to 4 2 6. These are the three vectors that are given to us, and there is one more column vector given to us, which is named w bar, namely w bar, and that w bar is given as 8 column, again a column vector with the elements 8 4 7. Now our aim is to our aim is to show that whether w bar is a linear combination of v1 v2 v3, so that it can be in the span of v1 v2 v3, or is it not a linear combination of v1 v2 v3, so that w bar is not in the span of v1 v2 v3. So that is the thing we have to find now. So I have considered a linear combination of v1 v2 v3 taken as equal to w bar. So I have equated w bar to a linear combination of v1 v2 v3 with the taking the scalars a1 a2 a3 from the set of real numbers, So w bar is equal to a1 v1 bar plus a2 v2 bar plus a3 v3 bar for some scalars a1 a2 a3. Now substitute the vectors, column vectors, whichever are given to us above, which are in fact they are v1 v2 v3 and w bar. All these four vectors are given to us. Now substituting all these vectors in this, we get like this. In the next step, we are just doing scalar multiplications by the scalars a1 a2 a3 to the column vectors v1 v2 v3 respectively in this manner, and got the resultant vectors as a1 0 minus a1 plus 2a2 a2 3a2 plus 4a3 2a3 6a3. These are obtained by using the scalar multiplications in the matrices. And on the right hand side we can see there is w bar with which is a column vector consisting of 8 4 7 as the entries. On the left hand side there are three column vectors, each of same order. So by using the addition of matrices concept, we can add these three column vectors and get the resultant vector as a1 plus 2a2 plus 4a3, in the next row a2 plus 2a3, and in the last row minus a1 plus 3a2 plus 6a3, and on the right hand side it is 8 4 7 as we have seen in the above step also. Now we can observe that there at this stage we are left with two same order column vectors equated to one another. That means these are two matrices of same order and they are equal. So using the equality, the concept of equality of matrices, equate these two column vectors by the corresponding by the corresponding elements in each column of these vectors on either side. We can get three equations, and those three equations are a1 plus 2a2 plus 4a3 is equal to 8, a2 plus 2a3 is equal to 4, minus a1 plus 3a2 plus 6a3 is equal to 7. These are the three equations obtained from by equating those two column vectors above. So these three equations are represent a linear system of equations in the three variables a1, a2, a3. So I am representing these three equations together by equation number 2. So this linear system of equations in a1, a2, a3 can also be written in matrix equation as in matrix form as ax bar is equal to w bar, where a is equal to, this can be so simply we can write the whole system of linear equations into as a simple equation in which is called matrix equation as Ax bar is equal to W bar, where we can see capital A is equal to the a 3 by 3 matrix or 3 by 3 column 3 by 3 matrix of with the columns 1 0 minus 1 2 1 3 4 2 6, and we can see X bar is the variable matrix with the variables a1 a2 a3 taken in column, so it is a column. X bar is a column vector of order 3 by 1, and W bar is already given in the problem, that is also a column vector given as 8 4 7 as the entries in it. Now consider the augmented matrix capital A W bar. The augmented matrix A W bar is obtained by taking the whole matrix A first, then in the fourth column take the column vector which is in W bar. So we get like this, it is 1 2 4 8 0 1 2 4 minus 1 3 6 7 as rows, 3 rows, and there are 4 columns, so it is a 3 by 4 matrix. Now at this juncture we want to transform this augmented matrix to echelon form, and for that we need to perform some elementary row operations on this augmented matrix, and I have chosen the first row transformation as R3 as R3 plus R1. So I want to add R third row and first row and write it in the third row, so that we can, after doing that, we get this matrix which is equivalent to the above augmented matrix. It also consists of 3 rows and 4 columns, where the elements are now changed in the third row, and we can see like this: 1 2 4 8 0 1 2 4 0 5 10 15 is the new matrix. And here we can observe that in the third row the elements are 5 10 15. 5 10 15 means we can divide, all these numbers are divisible by 5, so we can take the next row operation as R3 changed as R3 divided by 5. So in the next transformed matrix the rows can be seen like this: 1 2 4 8 0 1 2 4, and in the last row it is 0 1 2 3. As when we divide 5 10 15 respectively by 5, we get the numbers 1 2 3, and 0 is the first element which is already there. So R3 next the row transformation I have chosen is R3 changed as R3 minus R2. So do this row operation, which is R3 as R3 minus R2. That means subtract the second row from third row and write the resultant elements in the third row. So doing this, we can get the next equivalent matrix of the given augmented matrix as 1 2 4 8 as the first row, 0 1 2 4 as the second row, 3 zeros 0 0 0, and at the end it is minus 1. So 3 zeros minus 1 as the third row. So by our previous knowledge, by observing this transformed matrix, we can say that the last row, as it contains 3 zeros and a non-zero element at the end, this implies that the given system of linear equations in equation 2 is inconsistent, and hence it will have no solution. That means there will be no values for a1 a2 a3 which satisfy the equations linear system of equations in equation number 2. So now we have come to the conclusion by our previous knowledge that as the last row of this transformed augmented matrix consists of all zero elements except a non-zero element at the end, the linear system of equations in equation number 2 is inconsistent, and hence it has no solution. That is, there exists no scalars a1 a2 a3 from the set of real numbers which satisfy the equation number 1. So if there are no values for a1, a2, a3 in equation 1, we can say that W bar is not a linear combination of V1 bar, V2 bar, V3 bar. So that is how W bar is not in the subspace spanned by V1 bar, V2 bar, V3 bar, as the equation W bar is equal to A1 V1 bar plus A2 V2 bar plus A3 V3 bar has no solution. This means the meaning of this last statement is that W bar is not a linear combination of V1, V2, V3. It cannot be in the span of V1, V2, V3, where span of V1, V2, V3 is the set of all linear combinations of V1, V2, V3. As we are unable to write W bar as a linear combination of V1, V2, V3, it cannot be in the set span of V1, V2, V3. But span of V1, V2, V3 is a subspace of the given vector space. So that is how W bar is not in the subspace spanned by V1, V2, V3. Now we can move on to the next problem, and this is let W be the set of all vectors of the form minus A plus 1, A minus 6B, 2b plus a, where a, b, c, the scalars a comma b comma c are real numbers. Find a set. Our task is to find a set capital S of vectors that span W, or give an example to show that W is not a vector space. So our the task given to us is that capital either we have to show that there exists a set S of vectors so that that spans W. That means span of those vectors is equal to W. Or if we are unable to get such set S of vectors which span W, then we need to find a vector or give an example to show that W is not a vector space. So to get the solution of this, first of all consider whatever is given in the problem. So we are given that W is the set of all vectors of the form minus A plus 1, A minus 6B, 2B plus A, where A comma B comma C belongs to capital R. A, B, C are real numbers in this element. Then if this is the arbitrary element of W, then the set W can be written as W is equal to set of all minus A plus 1, A minus 6B, 2B plus A. It is a column vector of order 3 by 1 such that A comma B comma C belongs to capital R. So this is the notational form of W, where we can represent every element of W by a single arbitrary element of it, where A comma B comma C can take different real values to give the different elements of W. Now as minus A plus 1, A minus 6B, 2B plus A is an arbitrary element of W for A comma B belongs to R, consider that arbitrary element and resolve it into 3 column vectors, wherein they are scalar multiples of A, B, and so that the sum of those scalar multiples is equal to that arbitrary element. And here we can see minus A plus 1, A minus 6B, 2B plus A. This vector can be written as taking A common. We get the column vector as multiple of A as minus 1, 1, 1. This is obtained in this manner. See, in the entries in the left hand side column vector, we can see the coefficients of A. In the first entry is minus 1, in the second entry it is 1, and in the third entry it is 1. That is how on the right hand side, when we take A common, the column vector that is multiplied to A is minus 1, 1, 1, which are nothing but the coefficients of A on the left hand side column vector. and similarly taking plus b common, and this is plus b times 0 minus 6 2, where we can observe that 0 minus 6 2 are the coefficients of b on the left hand side. And also we are left with one more column vector, which is plus 1 0 0. There is no scalar multiple find here. How is that possible? Means, see here on the left hand side, in the first element, first entry, it is minus a plus 1, where in the fixed element 1 is present. So from 1, we can neither take a common nor b common. That means 1 is neither a coefficient of a nor it is coefficient of b. So that is how it cannot be taken in the scalar multiple of a or in the scalar multiple of b. So that should be represented in a separate column vector as 1 0 0, and it has no scalar multiple seen there. So this is the equation I have taken represented as 1. Now consider v1 bar is equal to minus 1 1, the column vector of which is multiplied to the scalar a. Let us name it as v1 bar. So v1 bar is equal to minus 1 1 1, and v2 bar is equal to 0 minus 6 2, and there is another vector v3 bar is equal to 1 0 0. Now consider the set capital S, which consists of all these three vectors. That means S is equal to capital S is equal to a set consisting of v1 bar, v2 bar, comma v3 bar. From the equation 1, we can see that minus a plus 1, a minus 6b, 2b plus a. This arbitrary element of w can now be written as equal to a linear combination of v1 bar, v2 bar, v3 bar for some scalars a comma b taken from the set of real numbers. That means every element as an arbitrary element can be written as linear combination. We can say that every element of w can be expressed as a linear combination of v1, v2, v3 for some scalars a comma b taken from the set of real numbers. That means w is equal to span of v1 bar, v2 bar, v3 bar, and that means we can say that w is equal to span s, as s is the set v1, v2, v3. And if we represent s by its vectors in it, we can have s is equal to the set consisting of the vectors minus 1 1 1, which we have named it as v1 bar, comma 0 minus 6 2, which is v2, and the other one is 1 0 0, which is v3 above. And this set S is a set of vectors that span w. That means every element of w is a linear combination of all these three vectors. Next, also we can claim that for some values of a comma b in equation 1, the 0 vector 0 bar is equal to 0 0 0 will be in w. So for some values of a comma b in this arbitrary element, which are the real values, we can substitute and get the value and get the column vector 0 0 0 as the resultant vector, and that is 0 vector, and we can now say that 0 bar will be in w, and hence w is a first of all w is spanned by the vectors v1, v2, v3, and also there is 0 vector in it, and that is how w is a vector space. Now moving on to the next problem, that is let w be the set of all vectors of the form 3. It is a column vector again, it is also of order 3 by 1. Now the variables in this which are the entries or elements of this matrix are 3a plus b, 4a minus 5b, where a comma b are arbitrary real numbers. We are asked to verify whether w forms a vector space. So now if the elements of w are of this form, we are asked to find whether w forms a vector space. For this, let us consider whatever is given in the problem first. So it is given that W is the set of all vectors of the form 3a plus b, 4a minus 5b. These are the three entries in the column vector of order 3 by 1, where a comma b are arbitrary real numbers. Here we can see that a comma b are arbitrary real numbers. They can be any real numbers from the set capital R. Now, taking by this information, we can form the set W in set builder form and write it in notational form as W is equal to set consisting of the column vectors 3a plus b, 4a minus 5b such that a comma b belongs to capital R. A comma b are real numbers. That means if W is defined so, we can say that 3a plus b, 4a minus 5b. That is an arbitrary element of W for a comma b belongs to R. So 3a plus b, 4a minus 5b. This is an arbitrary element. What is meant by arbitrary element? It can be any element of W depending on the value of a comma b, which are taken from the set of real numbers capital R. Now consider that arbitrary element. That means consider 3a plus b as the first entry, 4a minus 5b as the third entry. This whatever we have written on the left hand side now is nothing but the arbitrary element considered from the set W. And now I want to resolve it into column vectors multiplied by some scalars. So for that I have taken a common first. As the variable a we can see in the column vector on the left hand side, let us take that a common. Then we get a times 301. A times 301 as the first scalar multiple. And now take plus b common. Plus after plus take b common. And now it will be equal to b times 10 minus 5. How did we get this 301 vectors and 301 vector and 10 minus 5 vector? We can say that when a is taken common from the left hand side vector, column vector, we can see the coefficients of a in that column vector are, in the first entry it is 3, in the second entry as there is no a, we should consider the coefficient of a as 0, and in the third entry the on left hand side the coefficient of a is 1. That is how a should be multiplied with the column vector 301. And after plus b we have 10 minus 5. That means these are the coefficients of b which are considered from the left hand side matrix, and plus left hand side matrix or the column vector, and plus there is one more column vector on the right hand side which is 0 4 0, where there is no scalar multiple present. How can it be possible? Where did we get this column vector from? When we didn't take any scalar common, how did we get this 0 4 0 column vector on the right hand side at the end? This is justified like this. On the left hand side, if we see the column vector 3a plus b, 4a minus 5b, we can observe that the middle term, the middle element 4, which is 4, is neither a multiple of a nor a multiple of b. 4, the number 4 is fixed element and fixed number, and that is how it is neither the coefficient of a nor the coefficient of b. And if that is so, when we have taken a common, it cannot be present in the column vector which is multiplied to a. And in the same way, when we took the scalar b common, then also we cannot take 4 in the column as any entry of the column vector besides b. So that is how it has to be represented in a separate column vector. For that we have 3 column vectors seen in the right hand side, wherein the first column vector has the scalar multiple A, the second column vector has the scalar multiple B, whereas the third column vector has no scalar multiple. Also we can see that if 0 vector 0 bar is in W, then 3a plus b 4a minus 5b is equal to 0 0 0. Let us suppose that the 0 vector 0 bar is in W. What is 0 bar? As the W is consisting of all 3 by 1 column vectors, the 0 vector, if it is in W, then it should also be a 3 by 1 column vector with the entries 0 0 0, 3 zeros in column. Now, if the 0 vector is in W, the arbitrary vector should be equal to 0 0 0 for some values of a comma b taken from the set of real numbers. But this is never possible because the second element on the left hand side is 4, it is a fixed number, and on the right hand side the 0 vector consists of 0 as the second entry, wherein when we equate these two matrices which are column vectors, by the property of matrices the corresponding element should be equal, but 4 is never equal to 0. So this is an absurd thing. This is not possible at all. So by this I can say that hence 0 bar is not in W due to the middle term on LHS. That means 0 bar, the vector 0 bar, it can never be in the set W, because always the element of W has the second entry as the fixed number 4. So it can never have the element 0 as its second entry. So 0 0 0 is never be possible element in the set W. So that is how 0 bar, the 0 vector, is not in W. That means W cannot be a vector space. So our conclusion finally is that W cannot be a vector space. It can never be a vector space as the 0 vector is not existing in it. Now moving on to the next problem, which is the last problem in the span and subspace spanned by a set. That is the topic we are dealing with now. In this, the last problem is given like this. Let capital W be the set of all vectors of the form 4a plus 3b, 0, a plus b plus c, c minus 2a. That means this is a 4 by 1 column vector. So W is the set of all column vectors of the form 4a plus 3b, 0, a plus b plus c, c minus 2a, which are of order 4 by 1, as there are 4 rows and 1 column in this arbitrary element of the set W. And we can also say that these elements consist of scalars a, b, c, which are taken from the set of real numbers R. Our task is to find a set capital S of vectors that span W, or give an example to show that W is not a vector space. And do recall from the theorem that we have proved in the previous video lesson, that if v1 bar comma v2 bar are any two vectors of a vector space V, then span of v1 bar comma v2 bar will be a subspace of W. But so to show that W is a vector space, we need to find a set S of vectors which span W, so that W is equal to span of that set S, span S. And we can say that by the theorem just now I repeated for you, we can say by that theorem that W will be a subspace. That means it will be a vector space. But if it is not possible, that means if W is not possible to write as span of some set S, then we need to give an example to show that we need to find a vector to show that W is not a vector space. So this is the problem given to us to be solved in this last problem. Now let us move on to the solution, and let us take the whatever the information given in the problem first. So we are given that W is the set of all vectors of the form 4 column vectors, which they are 4 by 1 column vectors with the entries as 4a plus 3b, 0, a plus b plus c, c minus 2a, where a comma b comma c are real numbers. If this is so, then W, the set W in a set builder form can be written as, or W in notational form can be expressed as, set consisting of all the 4 by 1 column vectors of the form 4a plus 3b, 0, a plus b plus c, c minus 2a, such that a comma b comma c are real numbers. All the scalars a, b, c are reals. That means taken from the set R. So by this definition of W, we can say that some arbitrary element of W is of the form, any arbitrary element of W is of the form 4a plus 3b, 0, a plus b plus c, c minus 2a. This is considered as arbitrary element of W because by substituting different values of a comma b, which are real numbers, we can get different elements of W. So this is the arbitrary element of W, wherein a comma b can take any values of R to give the different elements of W. Now consider this arbitrary element and split it into scalar multiples, sum of scalar multiples. So now take the vector 4a plus 3b column vector of R, which is called arbitrary element of W, on the left hand side like this: 4a plus 3b, 0, a plus b plus c, c minus 2a. As we can see, there are three variables present in this column vector. Let us take a common, b common and c common on the right hand side and get some column vectors as multiples of these scalars a comma b comma c. And by the method that I have explained in the previous problems, in the earlier problems, adopt that method again and take a, b, c as common as scalar multiples to get some column vectors of order 4 by 1 besides them as multiples of a, b, c. And here we can see when we take a common, we got 4, 0, 1 minus 2 as the column vector multiplied to it. As we can see on the left hand side, the coefficients of a are 4, 0, 1 minus 2. Similarly, plus b, the column vector multiplied is 3, 0, 1, 0, and for c it is 0, 0, 1, 1. And here the scalar multiples a comma b comma c, as we know, are nothing but the real numbers. I have taken this as equation number 1. If we observe it, this is nothing but the whatever is there in the equation 1 is nothing but the linear combination on the right hand side. So some arbitrary element of W can be written as linear combination of the 3 column vectors on the right hand side with the scalar multiples a, b, c. So let us name these 3 column vectors as v1 bar, v2 bar, v3 bar. Then I can have v1 bar is equal to 4, 0, 1 minus 2, v2 bar is equal to 3, 0, 1, 0, comma v3 bar is equal to 0, 0, 1, 1. And I want to take all these 3 vectors in a set S, and that is how S is equal to the set consisting of v1 bar comma v2 bar comma v3 bar. If the 0 vector 0 bar is in W, then the if we suppose that the 0 vector is in the set W, then the arbitrary element will be equal to that 0 vector, so that 4a plus 3b 0 a plus b plus c c minus 2a is equal to 0 0 0 0 taken 4 times, as it is 4 by 1 column vector, which is as every element of w is a column vector of order 4 by 1. So now we have on both sides we can equate the corresponding elements and solve for a comma b comma c, and also we can see that all of them are nothing but the real numbers. That means the arbitrary element can take the values 0 0 0 for some values of a comma b comma c from the set capital R. That means 0 bar is in W, in the set W. So first of all, W is equal to span of V1, V2, V3 and by equation 1, and 0 bar, the 0 vector is also in W, and so that the conclusion we can draw from these things is that W is a vector space. So W is equal to, as W, every arbitrary element means every element we can generalize it. So every element of W is a linear combination of the vectors 4 0 1 minus 2 3 0 1 0 0 0 1 1, which are taken as V1, V2, V3 by us, and hence every vector in W is a linear combination of V1, V2, V3, and that means W is spanned by the spanned by the vectors V1, V2, V3, or we can say that W is equal to span of V1, V2, V3, or simply span S. So, and further we have seen that 0 vector, the 0 bar is also in W. So by all this we can say that W is a vector space. So that is how we have seen that in the problem the sets given are in some cases they are vector spaces, and in some cases they are shown that they are not vector spaces by some reasons. So go through all these problems and get the concept of span and subspace spanned by a set, the concepts very well, and get them clear while solving these problems. So with this video lesson we have finished off the topic span and subspace spanned by a set. In the next video lesson we are going to learn a new concept, a new term, that is null space. So in the next video lesson we will go through the term null space, its concept, definition, examples and problems based on null space. Okay, with this I will sign off. We'll meet in the next video lesson.